All right, guys. Sorry, I'm running a couple of minutes late. I had a problem with the juice. I lost my juice. That one doesn't work. It's not right. I left my juice bottle somewhere. I'm going to find it though. It'll come back to me. So I'll begin with a scripture today here. So this is John chapter 14, verse 6. It says the following. And Jesus said to him, I am the way and the truth and the life. No one comes to the Father but through me. So it's pretty straightforward, I think. I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. Thank you for your creation, that we can study it. Help us to glorify you what we do and understand a little bit more about energy and work and so forth, Lord. In my prayer, Lord Jesus. Amen. All right, so let me get straight into it here. I need to explain to you guys how we can calculate the potential energy function from the force. So I wrote down an example last time, essentially by magic. I'd like to kind of explain to you the method. First of all, I should give you a definition. So here's the definition. F is conservative force field on S if F is equal to minus the gradient of U on S. Now here, the gradient of U, it could be partial U, partial X, partial U, partial Y. This would be like n equals to 2 case. But the gradient in 3 dimensions has a z derivative as well. All right, and I guess I should mention, in 1 dimension, what's the gradient? It's very silly. Gradient of u is just equal to du dx. And then n equals 1 case. So like, the conservative, a force is conservative in the 1-dimensional context. This just looks like F equals to minus du dx if you're in n equals to 1. Right? Okay, so how do you actually find the potential energy function? So here U is called the potential energy function. The reason for this terminology will become more clear as we go on today. So let's look at an example. Suppose your force field has the form, let's say, 2x plus y, comma, y cosine of y squared plus x. All right. The question then is this a conservative vector field? All right. So then that question basically the question's begged here is, can you find a potential energy function? All right. So let's write down what we need to do. We need to find if we can solve partial u partial x equals to minus 2x minus y. And we also need to solve partial u partial y equals to, let's see here, minus y cosine y squared minus x. The minus being there because of, well, again, this will become clear as we go on today. But, so how would you, here, well, let me just tell you how I solve these is I integrate both of them, all right? So I integrate this one with respect to x, like anti-differentiate with respect to x, holding y fixed. This to me says that I should try u equals to like minus x squared minus xy. And then I've got some constant, which in principle is a function of y, all right? Integrating the second one, that tells me that my potential energy looks something like Let's see here. So minus the sine of y squared. See, because if I differentiate sine of y squared with respect to y, I get back, oh, wait a minute, do I get this? I would get back minus cosine of y squared times 2y, right? Is that right? So I should do what? Yeah, I should divide by 2. If I divide by 2, now if I differentiate that with respect to y, I'll get this, right? Oh, but also minus xy plus c2, which is possibly a function of x. So I'm doing an integration. I'm integrating with respect to y, holding x fixed in the second line. I'm integrating with respect to x, holding y fixed with the first line. When you do this, you have to use some common sense, all right? You look at both, all right? And if there's anything that's common to both, you don't need it twice. You only need it once in the answer. So basically, you take these two and you merge them, and that's your answer. So here the answer would be, what will work for us is u equal to, looks like we need a minus xy minus x squared minus 1/2 sine of y squared. All right? And then, of course, you could add a constant to this. This is the thing. Because the gradient is formed by taking derivatives, you guys know what happens with derivatives. If we have a constant, what happens? It differentiates to 0, right? So there's always a certain flexibility in your choice of potential energy. You can always like redefine where 0 is for the potential energy by adding a constant. I'm just going to I like to just leave it like this. You know, this means what? What's u of 0, 0? This makes the potential energy 0 at the origin. Yeah?
Is it minus 2xy instead?
No, it is not. This is what I was just talking about. We have to merge them. We don't just add these answers. We have to think about it. So if you think about it, when I take the gradient of this expression, right, that one term, minus xy, with the x derivative, will produce a y, and with the y derivative will produce an x. So this one term gives me both of these guys in the gradient process. We only need one of them. That's why that's the great question. That's the point of this example, is that you don't put a 2 there. Now, if you don't like this method, there is a more laborious and slow way. The slow way is integrate one, and then plug it into the other one and integrate that. And if you do that, you will discover also when it's not possible to find something like this, right? Not every vector field is conservative. There are some that are not, all right? So, does that make sense? Let me do another one that's really easy. Example 2, what if your force is 0, 0, minus mg. We like this force, right? 3-dimensional, what's this? Gravity, right? So this is the equal to minus the gradient of what function? So we're trying to ask the question, we want, basically the only thing that's interesting here is that we need partial u, partial z to be equal to mg. Notice I'm absorbing the minus. So I think pragmatically speaking, guys, it's actually a little bit easier when you're trying to solve for the u. Instead of looking at the definition, I think it's probably a better habit when you're trying to find the u to instead repackage this as the gradient of u is equal to minus f. See, that's what I'm actually using for setting up this and now that, all right? So minus the force gives me a minus mg for uz. And how about the x, and there's no x and y dependence. So basically, this suggests to me I can just put mgz here, right? mgz will work. If we calculate the gradient of mgz, this would be equal to minus partial x of mgz, partial y of mgz, partial z of mgz. also known as what? 0, 0 minus mg, woohoo, which is what we want, right? So in short, to summarize, this one shows us that the potential energy for gravity close to the surface of the Earth, we could use mgz. There's your potential energy due to gravity, taking z as the up and down, and this defines potential energy to be 0 at z equals to 0, all right? Okay? All right, so I'll show you some more examples of this, but before I do, I think it's good for us to stop and appreciate the physics of what's going on here, okay? So let me talk to you guys about a theorem, and this is the fundamental theorem of calculus for line integrals. And it says the following. It says that the integral over a curve of the gradient of a function, all right, dot dr, is simply equal to the value of the function. And I need to talk about this curve here is a curve that begins at the point P and ends at the point Q for the sake of discussion. So it's equal to f of Q minus f of P. This is the fundamental theorem of calculus for line integrals. It simply says that if you're calculating the work integral of a gradient, you just take the difference of the function that's being gradiented, I guess you could say, differentiated. Yeah. Yes, sir?
Sorry, what's a gradient again?
Right here. So the gradient of u in 2 dimensions is a vector, partial u, partial x, comma, partial u, partial y. Or for 3-dimensional, it's this, this, and this. If you're asking like what it is more fundamentally, that will be answered in Calculus 3. But I can tell you more in office hours if you want to know. I'll tell you this much, since you asked. For example, if I take f of xy equals to x squared plus y squared, right? I calculate the gradient of f. That gives me 2x comma 2y, all right? So to understand the significance of the gradient, it's helpful to look at what is characteristic of the function x squared plus y squared. So what is x squared plus y squared? You say it's a circle. That's right. It's a circle if we think about its level curves. All right? So like the level curves of x squared plus y squared are circles. Yes, indeed. So these are x squared plus y squared equals to r squared, right? If you like, they're level r squared curves for this function. If you plot the gradient of f, what's it look like? This is a vector field which is always pointing outward, so it looks like this. All right, so it's going outward, and it's always going radially away from the origin. That's what this thing looks like. So it's a vector field. It gives you a force. It gives you a force vector at each point in space you can think of it. If you want me to explain to you what the gradient is geometrically in a nutshell, it points in the direction in which you want to level up. So these are level curves, level r squared. The gradient vector field points in the direction to go to higher levels. So the gradient field tells you where to level up. However, in physics, because we put a minus in the potential energy function, it tells you not where to level up, but where to level down. In other words, the gradient of the potential energy function, because we put a minus there, it points in the direction of decreasing potential energy. So that's where the force wants the thing to go. If we're talking about the net force will cause a motion which decreases potential energy, because nature always tries to decrease energy to go to a stable state eventually. That's the larger idea here. I don't know if that helps or not, but that's what a gradient is.
So it wouldn't be something like almost like the derivative of like a 3-dimensional curve?
Well, it is a kind of derivative, but we're talking about a function of 2 variables, so the derivative is not just a slope, it's something more complicated, yeah.
And just to clarify, what u is just the function.
U is the potential energy here.
I'm saying like just calculating the gradient in general. We just integrate or start partial differentiating x squared plus y squared with respect to all the variables.
Yes, yeah, exactly the gradient. We just, the x derivative for the first, the y derivative for the second. If you have a function of 3 variables, then there's 3 components. But then you have to think about things in 3 dimensions. If you take a function of 3 variables and you set it equal to a constant, then you're talking about a level surface. Like if I add a plus z squared, then we're talking about spheres. And we'd have a 3-dimensional vector field, which would be pointing outward from the origin radially. But this example kind of generalizes. Yeah. You know, this is important, especially for you electrical engineers, because next semester we will soon be talking about the context of like potential energy per unit charge. Then the potential energy per unit charge is exactly the voltage function. And minus the gradient of the voltage function will point in the direction of the electric field, which will become important to you because, well, you're electrical engineers. Or you're just engineers who, you know, want to have like a proper science education. Also possible. Let's see here. So, actually, preferable. Let's see here. So, going on here, I'm not going to prove this, but this is easy enough to prove. And what's more interesting is its application. So, check this out. If, this is the fundamental theorem for us, really, if the net force is conservative, right, then energy is conserved. If the net force is conservative, then energy is conserved. Now let me try to bring, you're like, well, you haven't even told me what energy is. That's true. Let's do a calculation. Let's work it out. So last time, we figured out the work energy theorem. What did the work energy theorem say? Last time, we worked out that the work done by the net force was the integral of F net, right, dot dr, and we worked out that that was equal to the change in what? The change in the kinetic energy, right? If you like, you could say KE2 minus KE1. And so the situation we're talking about here is we've got some kind of particle that's going from, say, point 1 to point 2 over some curve, let's say C, and some net force is accomplishing this motion, all right? So in that situation, the work done by the net force is equal to the change in the kinetic energy. What was kinetic energy equal to? You guys remember? 1/2 mv squared. Very good. You guys got it. Now, if the net force is also conservative, then that means that this is also equal to minus the integral along the curve of the gradient of the potential energy function dot dr. All right? But by the fundamental theorem of calculus for line integrals, keep the minus out, we get minus parentheses like u of 2 minus u of 1. Right? Or if you would like, I can put it in the notation that Dr. Budaras hates, and I accept his hatred. He's allowed. He's more of a physicist than I am for sure. So we got minus PE2. Yeah, I only have a master's in physics, so you really should call me Mr. in here. Plus PE1. Right? Or if you like, you could say that this is equal to minus the change in the potential energy. So we have the situation, if the net force is conservative, the work done is either the change in kinetic energy or it's also minus the change in the potential energy. I almost never use that. I find it much more interesting to take these two equations here and solve them. Because those two equations, if we solve them, what we get is that the kinetic energy for 1 plus the potential energy for 1 is equal to the kinetic energy for 2 plus the potential energy for 2. Which is just very cool, because then we can make a definition. The total mechanical energy, which we'll call E, is equal to kinetic energy plus potential energy, or for our current notation, 1/2 mv squared plus u, which for us is usually a function of x and y, or possibly x, y, and z if we're thinking three-dimensionally. So this is the total mechanical energy. The total mechanical energy is the sum of both the potential and the kinetic energy. And it has to be conserved if the net force is conservative. we will soon see in upcoming lectures that this allows us to solve a vast variety of problems with great ease. We've already been flirting with this. The truth is, every time we use the timeless equation, it's exactly this. All right? That's the truth. All right. Let me go on here. So, natural question to ask is, so for example, what if you want to, let's look at example 1, right? Take example 1. Let's use it for something. So let's let's see here. Example, where am I? 3. Example 3. For the force from example 1, find work done by F for C, which goes from, let's say, the point 1, 2, 3 to the point I don't know, pi, not pi, what am I talking about? 0, 3, 7, whatever. All right. So what's the work done? So here's a pro tip for you. The next test, if I ask you to calculate the work done by a force, all right, but I ask you to calculate the work done by a curve, right, and I don't tell you the parameterization for the curve, right? I don't tell you the trajectory that you're following. Think about last class. To calculate the work done, we had to plug in specific x equals x of t, y equals y of t, z equals z of t to do the integral, right? I've given you none of that. I've just told you that we've got this curve that starts at the point 1, 2, 3 and somehow ends over at the point 0, 3, 7. So I just want to think of those 2 points as like the initial and final points here. All right, so we use the part of the theorem here, which is minus the change in the potential energy, right? So that's minus u of 0, 3, 7 plus u of 1, 2, 3. But what was my formula for u? You guys will have to remind me. U of x, y, z equals what? I remember a minus xy. I'm remembering like a minus 1/2 sine of y squared. Is that right?
Minus xy minus x squared minus 1/2 sine y squared.
And there's a minus x squared as well?
Yes.
Is that it? All right, so that's the potential energy function here. All you have to do then is, well, there's no z? Oh, I'm an idiot. Is this a 2-dimensional example? I really need to get glasses. Let me fix it. Here. 1, 2. Sorry, 7. So sorry. Sorry, 3. Sorry, 7. You're gone.
Just a massacre.
It's it's a massacre of the 3rd dimension. Let's see here.
We didn't deserve the 3-dimension Alpine squash.
There you go. Just trying to go off the bounce. I have got it off that table before. It has happened. It's possible. Okay, so plug it in. What do you get? Minus 0 times 3 minus 1/2 the sine of 3 squared. There's my u of 0, 3. I better put a parenthesis here so I don't. That's a minus, which gives me a what? A plus that. And then plus what? Parentheses u of 1, 2, so I get minus 1 times 2 minus 1/2 sine of 4 minus 1. If I haven't made a stupid sign error here, I've got 1/2 sine of 9. That gives me a minus 2, minus 1, which is minus 3, I believe, minus the 1/2 the sine of 4. So there you go. That would be the work done. Obviously, to be more physical, we ought to put in units and things like that, but I'm trying not to clutter these examples any more than they already are at the moment.
You're getting into the
What's that?
for the x squared.
Have I missed my x squared term?
Oh wait, no, this is 0.
Oh, but you're right. The x squared term does matter. Did I do it?
It goes
Oh yeah, I did. No, but I did do that here. Check this out. So the x squared term was, oh, you're talking about the first term. Yeah, it was 0 on the first one, but it is this minus 1 over here. All right? Yeah? Okay. Let's see here. Let's do something a little bit easier. How about a constant force? So example 4, suppose you've got the constant force F naught equals to, let's say ABC for the, just keep it nice and simple. Is this a conservative vector field? What do you think? In other words, can you write this as minus the gradient of some function? Let me get us started. Let me suggest that you can do, to get that A, I need a minus AX minus BY minus CZ. That's what I get from integrating partial U partial X equals minus A, partial U partial Y equals minus B, partial U partial Z equals minus C. Listen, it's anti-differentiation, right? So the proof is in the pudding, so to speak. I mean, we say that? I don't know if we say that anymore. Nobody eats pudding. If you took the gradient of that, though, you should see that you get minus ABC, right? Yeah?
Do both negative signs belong inside and outside?
Yes, they do. So U of XYZ is equal to minus AX minus BY minus CZ. Let's try it out. What's partial U partial X equal to? What's partial U partial Y? What's partial U partial Z? Partial U partial X minus A, partial U partial Y minus B, partial U partial Z minus C. So all these things together tell us that the gradient of U is minus A minus B minus C, which tells me then that minus the gradient of U is equal to ABC, which is what we want because that is the given constant force. So yes, a constant force is a conservative force. Hooray! Not surprising. Constant forces are super easy. Too much. Check this out. So if you want to calculate the work done, say from point 1 to point 2 of a constant force, right? Then if you want to, we could calculate it with formal nonsense. Check this out. So pull the constant vector outside the integral. What do you think the integral of dr should be from P1 to P2? If you're adding up all the little dr's going from point 1 to point 2, what is it? It's the net change in r, right? It's exactly P2 minus P1. So this takes us back to the start when I talked about what is the work done by a constant force over, a displacement, a finite displacement. there's a other formula for this, of course. We could say it's F naught dotted with the line segment that goes from P1 to P2. But if you wanted to derive this with less formal nonsense, you could just as well do what? Calculate the work done by the integral of F naught from P1 to P2 to be equal to minus U of P2 plus U of P1. What would that be? That would be, according to the formula here, minus AX2 minus B. Actually, it should be a plus, right? Because minus minus is a plus. And that's nothing more than ABC dotted with the difference in the coordinates of x's of P2 and P1, which of course is nothing more than the line segment that goes from point 1 to point 2, as we would expect. So, just this is another way you could look at this problem here. I'm not telling you anything terribly exciting in this example. I'm merely telling you that for a constant force, we do have a potential, and it's pretty easy to write down. Now, I don't mean to give you the wrong idea. There are force fields where the potential energy is a little bit harder to derive. Yeah, they're not all that easy. And it's helpful to have a criteria which helps you know when it's possible and when it's not possible to find a potential energy function. See, because not every vector field has a potential energy function. So this theorem that I'm about to write here is helpful for us. Theorem. For a vector field F, the following are equivalent. Number 1, F is conservative on S. All right. And by that, we mean that F is equal to minus the gradient of some potential energy function on the space that we're considering. That's one characterization. Another characterization is that F is path independent. Path independent on S. All right? Think about it. If we can calculate the work done for a conservative vector field, right? Just as equal to what? Minus the change in potential energy. What does that depend on? It only depends on the endpoints of the path that we're calculating the work, right? So it doesn't matter which path connects the endpoints. That's path independence. All right, so path independent. And then this one's new. 3, the integral on a loop of f dot d dr is equal to 0 for all loops in S. And for this one's a little bit technical. I include this one for the sake of what's the word? Full disclosure. But I don't think I've not assigned you any homework on this. I don't expect you to be able to do this. It's just for context, okay? But if S is simply connected, then you can add to this the curl of F is equal to 0. Again, I haven't assigned you any homework on it or anything, so you can ignore 4. I wouldn't test you on 4, and here's what I'm trying to say, all right? So what this means is if you have a vector field and you calculate the work done by the vector field around a loop, and if it's non-zero, then that means that the vector field's not conservative, all right? So, like, a good example of that if we calculate for the vector field f equal to, let us say, minus y over x squared plus y squared, comma x over x squared plus y squared. So this is a vector field. We can calculate the work done by this vector field, say, around the unit circle. So that would be x equals cosine t, y equals sine t, right? So we got dx is minus sine t dt, dy is cosine t dt, and this would be for 0 less than t less than or equal to 2 pi. That gives us a parameterization, a trajectory which goes around the circle, unit circle, one time. If we calculate the work done by this vector field along that curve, all right, what we get is, well, apparently the integral of minus y dx plus x dy over x squared plus y squared along the curve. But can you guys tell me how's that work out? What is x squared plus y squared for the unit circle?
1.
That's 1, right? And what's minus y dx? So we get integral from 0 to 2 pi of, let's see here, minus sine t times minus sine t dt plus cos t times cosine t dt, all divided by 1. Well, this is a very boring integral, it turns out. It looks kind of scary to start with, but actually after the dust settles, you got sine squared plus cosine squared dt. Okay? Yeah, that's just, so this is dt. And this is apparently 2 pi. So can this vector field be conservative? If you believe my theorem, apparently not, right? Because we just found an integral around a loop. A circle is a loop. A loop is just a curve which begins and ends at the same point. So that, see, if there was a potential energy function for this force, you could pick any point on the circle and say it's the ending and the starting point, right? So then the change in potential energy must be 0, and yet it's not. It's 2 pi, right? Well, minus 2 pi, I suppose, if this is the work done. What gives? Why did this happen? What's the deal with this vector field? Well, let me tell you the secret. If you calculate the gradient of the inverse tangent of y over x, what would that give you? You guys know how to differentiate inverse tangent? I know you do. You're in the middle of calculus too. So that's 1 over 1 plus y squared over x squared. Chain rule, so minus y over x squared, comma, 1 over 1 plus y squared over x squared. Chain rule, 1 over x. Clean it up. You've got minus y over x squared plus y squared, x over x squared plus y squared. What's the problem? Doesn't that show it's conservative? Oh, fair enough. So, I mean, we could put a minus. I mean, fair, you got a good point. We could put a minus though and get the minus, right? Yeah. Thank you. Sorry. My calculus 3 is showing, let's see here, minus, and let me just leave it. Let me not do that. I mean, the calculation's fine, but the, let's see here. So how can I say this? Minus the gradient of minus the inverse tangent. It's so annoying, the minus from physics. It just is what it is, but, right? You'd agree? I just need to do like that, okay? So that means that this is my quote-unquote potential energy function, right? The trouble is, what's the domain? Like, what space is this vector field defined on? 0 to 2 pi. Let me ask it a different way. Where does that vector field not make sense? What's the problem here? Yeah, 0. X equals to y equals to 0 implies, right? I mean, it blows up there, right? So technically speaking, this vector field's only defined on what's called the punctured plane. You're missing the origin, right? So yeah, I can find that potential energy function, but where is inverse tangent defined? Where does it have trouble? Well, how about this right here? X equals to 0, oops, right? So inverse tangent really is only good for this piece right here. All right? So that works as a potential energy function for over there, but it doesn't work for the whole plane, right? It turns out, if you study this carefully, you can build an angle function, because what we're really looking at is the change in the angle function. Inverse tangent of y over x is the angle. The reason we got 2 pi is because the change of the standard angle all the way around the unit circle in the counterclockwise sense is 2 pi. This is inescapable, no matter how you define angle. If you go all the way around the circle, the change in the angle is 2 pi. So no matter how you play games with inverse tangent or inverse cotangent, however you slice it, you'll always get back this 2 pi, which goes to the fact that you cannot define a potential energy function that's defined on the totality of the punctured plane for this vector field. So I know, you know, we sometimes like to do mathematics where we're like kind of careless about domain, and we can get a long way without caring about domain. But at some point you pay the price, and like this is all about domain. What's going on here? But anyway, let me get back to the other examples here. So I just wanted to give you guys an example of a vector field which is not conservative. Actually, this is like the most subtle example possible. So I could have found something a little bit less draconian for a non-example. How about this? Example, where am I? Example 6. We could look at something like f equal to, I don't know, y, comma, y plus x, for instance. All right. So let me just see if I can. Actually, I don't know if I have enough time for this. We'll see. So I want to go from here to here to here, that curve. So let's say this is 1, 0, and let's say this is 1, 1. And I want to contrast it with going just directly. So this is going to be like C1. This is going to be like C2. Both curves end and start at they begin at the origin, and they go to 1, 1. All right? So to calculate the work done along C2 of f dot dr, I can integrate from like 0 to 1. So this C2, if you want equations for that, we could put x equal to t, y equals to t for 0 less than t less than 1. So I have integral from 0 to 1 of t comma t plus t dotted with dx, so that's 1, 1 dt. So that would be the work done along C2. So we'd have integral from 0 to 1 of apparently 3t dt. That works out to 3/2. The work is 3/2 along C2. On the other hand, the work along C1 would be the integral from 0 to 1 Now C1 is x equals to t, y equals to 0. So we have x equals 0, comma, t, dotted with 1, 0 dt, plus the integral, say from 0 to 1 of this guy over here. We have x equals to 1, y equals to t. Again, 0 less than t less than 1. So x equal to, well, x equal to 1, y equal to t. So I got t, comma, t plus 1. The velocity here is 0, 1 on that vertical line segment. And so we've got integral from 0 to 1 of 0. Well, that's easy. Plus the integral from 0 to 1 of t plus 1. Now, if this works out to be the same, I'm going to be very annoyed. It better not, though. This is 1/2. Oh, come on. Seriously? Oh, my. Ah! Ah! What's that?
Is that because it's the same page, though?
This is not a conservative vector field. I don't think. Oh, it is. It is a conservative vector field. Son of a gun. Look at that. What's this, the gradient of what? Come on. Look at this. What do? Minus what? Minus xy plus 1/2, rather minus 1/2 y squared. Is this not a conservative vector field?
That's a very nice conservative.
It's a conservative vector field. So of course the triangle path and the, like, yes, they're going to give us the same answer. Ah! I'll try to give you a better example next time. There are problems in your homework where I have, like, part A, work out the work along this path. Part B, work out the work along that path. The point of those is if you get different work along different paths, it's not path independent. Therefore, it is not a conservative vector field. That's the point of that homework problem, which I was trying to illustrate. I have failed. Ah!